we have done on packed bed, right. Now, another application of this fluid flow typically in packed bed is called fluidized bed, right, or flow through fluidized bed, right. For example, let us go to that 20. Yeah. So, flow through fluidized bed. Now, what do you understand by that? Right? That is the fundamental thing what we understand by fluidization of a bed. We will come to application afterwards, but before that let us find out, let us understand what we mean by fluidization. The other day we had said, if you remember in packed bed, that if suppose you have a container like this, right, and in that container if it is perforated, right, and if we have full of say peas or similar kind of material, right, like this, if we assume that it is full up to this, right. Now, say a gas is being passed through this, right, or a fluid is being passed through this. Now, this fluid you can pass at any velocity, say at a very nominal or low velocity of 0.1 meter per second. So, what will happen? This will go, and there is a term called tortuous. So, tortuous path, that tortuous path is nothing but when it is moving like this through the vacant or through the void space between the particles. So, we have some void space between the particle, right. So, that void space will be utilized by this gas, and when it will go, it will move like this. Say gas is passing through this way, this way, this way, right, it will pass out, and this is called tortuous motion or movement of the fluid, right. Otherwise, had it been no particle, then this gas could have been gone through like this straightforward, but it is not. It has to move through the space available when the velocity is low. Now, if we go on increasing say from 0.1 to 0.2, then 0.3, like that 0.4, like that we are going increasing the velocity. So, what will happen? After some time, these particles will feel that someone is making a thrust from the bottom of this, right, and then they will start moving a little this adjusting this like that. So, there will be some velocity when that may be 1 meter per second, that may be 2 meter per second, that all depends on the gas used, the many other factors, the particles, many other, and packing all. So, at some higher velocity, what will happen? These particles, they will feel that some thrust is coming from the bottom, and they will start gradually a little movement in the up, right. So, there will be some velocity when these particles will move a little, like from here, if the particle is getting shifted to this layer, right. So, these particles will be shifted a little like this, like this, like this, like that, like that. So, there will be some increase of the length of the original packed bed, right. Originally, we had the packed bed length, say this one, as say before the movement of the particle, it was say L. Now, when this has started and when the onset of fluidization, we call it to be onset of fluidization. So, when onset of fluidization occurs, then this height will change it to LMF, right. That is called the length under minimum fluidization velocity, right. So, what I mean that these particles, they will gradually move from this, and all the particles will have a floating like a, they individually they are floating on the gas, right. Obviously, as we have said that you have to increase the velocity of the fluid. Now, the moment you increase the velocity of the fluid, there will be increment of the cost for making that higher velocity. Then if that be, then why do we do? What is the need? The need is that the moment you are doing this, as we said that each particle, say this particular particle, right, it will have, if we bring down to this, it will have all around it that gas, all around it that gas. So, the entire surface area of the particle will be exposed to the gas. Now, this gas could be hot gas, this gas could also be cold gas, right. So, either for heating or for cooling, if you are using that gas or fluid, then heat transfer will be better, because surface area now you got exposed all the entire surface, right. This is not for a typical one particle, this is for the entire set of the particle, right, the entire set of the particle which are here. So, all the particles, they are now exposed to the environment of that gas, either hot or cold, whatever you are doing. So, this improves your heat transfer drastically. There, this addition excess of this money which you have invested for creating that higher velocity is compensated, or maybe you are getting some profit out of that by increasing the heat transfer there and thereby decreasing the heating or cooling time. So, you are buying the time by increasing the velocity, right. Now, this set is known as, this condition is known as the velocity at which these particles will start just floating on the medium, that is the fluid by which you are heating or cooling, or through which it is that medium which is passing through these particles, right, that will be the minimum fluidization velocity. So, minimum fluidization velocity is that when your particles have started dancing. This is what you can call it to be dancing, as if this somebody. I hope you have seen during your when you were a child, somewhere in some parties or some functions, you might have seen that a jet of water is coming out, and on the top of it there is a ping pong or the tennis kind of ball, right, and which is floating on that, right. So, that you have given the jet of this water, and depending on this force which you are applying, that particular ball is floating and dancing on that, right. Water particles are gradually hitting on the sides and it is dancing like that. So, these particles also starts dancing on that environment, and the velocity at which this dancing or floating of the particles take place, that is called the onset of fluidization, and the velocity corresponding to that is called minimum fluidization velocity or minimum velocity for fluidization, right. For example, I have taken this from, of course, net or internet, which is available. So, here if you look at, right, this is a zip file. So, it will go undoing. So, gas is coming, these particles are there, you see when there will be a beginning. So, this gas is moving, right, and gradually it is taking, this is one gas only shown, one, right. So, if you assume that you are passing all along, all through, so gas is all coming like that, right. So, then what will happen, these particles will start dancing. So, that the bed and the height of the bed also is getting increased, right. This is a typical example, right. So, just to show that yes, these particles are gradually, I am not saying they are moved away, normally they are not moved away, right. So, that we had told you earlier that pneumatic conveying, right, pneumatic conveying we had said, and in that pneumatic conveying you are taking one particle or particles from one place to other place. So, that is conveying by pneumatic condition or pneumatic flow, but this is not that, you are not conveying the particles. What particles are doing? They are just dancing on that fluid, just floating on the fluid, right. This is that example of that. Okay. So, this is that bed, originally it was like this, and now when it has started and this all the particles, if they are moving or floating, then the height will be a little increased as we have shown it to be here, right. So, then let us see that how we have said this. We have said this, that flow in fluidized bed, that is fluidization. What is fluidization? Whatever we have said, that is jotted down in a language or in a concise way. So, what is that? According to Ergon's equation, when velocity v of a flowing fluid increases, the pressure drop also increases. You remember Ergon's equation, we had said it was delta P rho, right, delta P rho, and then it was by delta P rho by yeah, it was like this, G prime square, right, into phi s dp by delta L epsilon cube by 1 minus epsilon, that was 150 by NRE plus 1.75. This was Ergun's equation. Right. So, delta P rho by G prime square phi s dp by delta L epsilon cube by 1 minus epsilon is equal to 150 by NRE plus 1.75. This we said to be the Ergun's equation. So, according to this Ergun's equation, that as the velocity is increasing or velocity through the particles or backbed is increasing, the pressure drop also increasing. This is delta P, and in this G prime we have rho v, right, rho v here. So, as the delta P is in velocity is increasing, delta P is also increasing, remaining say other things remain same. If that be true, then delta P is increasing, this rho goes there. So, as this is this V goes there. So, as delta P is increasing, V prime or V prime is increasing, delta P is also increasing, right. So, when velocity reaches this is pressure drop also increases, this is true. So, when a velocity reaches a critical value, the pressure drop multiplied by the cross sectional area of particles, that equals the gravitational force. Obviously, that the pressure drop, this is the delta P, right. This pressure drop multiplied by the sectional area CSA, cross sectional area, right. This must be equals to the gravitational force, right, because gravity is pulling like this and this force is trying to build or move it, right. So, when the velocity reaching this condition, that the velocity is such that the pressure drop multiplied by the sectional area delta P times CSA is equals to the gravitational force, right. This condition we call the onset of the fluidization, when delta P times the cross sectional area this is equals to the gravitational force, right. So, at this when this is applied or when this is applicable, this situation arises, that situation is known as onset of fluidization. That means, any little increase in the velocity will allow the particles to move or to dance or to rather move is the right word. So, it can also be said as dancing, as it gave the example of that ping pong ball or table tennis ball on the jet of the water, many places you might have seen. So, that situation, that the pressure drop multiplied by the cross sectional area, that should be equals to gravitational force, and that situation when the velocity is such that this condition holds good, that condition is known as onset of the fluidization, right. So, we have understood this, and this is the onset of the fluidization and particles begin to move. The fluid velocity at which the particles begin to move is the minimum. The fluid velocity at which the particles begin to move is the minimum fluidization velocity, right. So, that is what I said earlier when giving the example, that when you are having a 0.1, 0.2, 0.3, 0.4, likewise you are increasing your velocity. So, in the beginning nothing is happening, after some time okay, there could be some this or that particles started just feeling that okay, something is, some thrust is coming, and then we will attain that velocity when this situation or this condition, that delta p times sectional area must be equals to the gravitational force. When the velocity corresponding to that attains, then we call that it is the onset of fluidization, and the fluid and the particles will start moving, or as we said, it is the dancing of the particles. The velocity at which it is happening is called the minimum velocity of fluidization or minimum velocity for fluidization. Velocity below that it will not fluidize, right. Above that obviously it will fluidize, and in that case some more particles may flow or may rise, or if you go on increasing the velocity, then at certain time that these particles may be transferred to some other, which was in our case earlier as the pneumatic conveying, but we are not going to that extent, right. So, the velocity at which the particles have started dancing or moving is called the minimum fluidization velocity. Okay. And the velocity at which the particles begin to move is the minimum fluidization velocity or V dot mf based on the empty cross section of the tower. The porosity of the bed at the onset of fluidization is known as minimum fluidization porosity, right. So, as we said, when we had initially up to this, there was a porosity, and this porosity, if it is epsilon, then when the porosity when the fluidization has started, corresponding to and the height was here L. Now, the new height has become LMF, that is the height, bed height corresponding to which the fluidization is occurring, that is called the minimum fluidization height, right. And this minimum fluidization height corresponding to that your void fraction, the void fraction which is there, or the gap between the particles, that is the void, right. The gap between the particles which is there, that is called epsilon m f, or the minimum fluidization or minimum void fraction when the fluidization has started, right. So, the porosity of the bed on the onset of fluidization is the minimum fluidization porosity or epsilon mf, right, epsilon mf prime, because we have denoted that when there was no fluidization, if there is delta epsilon, if the porosity and corresponding pressure is delta P, corresponding bed height is say L or H, whatever you call, say L, and when and the velocity is V prime based on the empty cross section. If that be true, then when we have started, we have obtained that fluidization, that corresponding velocity is Vmf prime, then corresponding the void is epsilon mf prime, corresponding length is LMF or height of this is LMF, corresponding pressure is delta P mf, right. So, all these parameters are getting changed depending on your this fluidization condition, right. So, when fluidization condition appeared, that time all the parameters like length or height of the bed or porosity of the bed or velocity in the bed, all these are getting changed, and corresponding this we are denoting as MF or under minimum fluidization conditions, right. So, we see here that the porosity of the bed at the onset of fluidization is minimum fluidization porosity or epsilon mf prime, and the height of the packaging at this porosity is L mf. Now, further increase in velocity results in the particles being thrown upwards and the bed resembles boiling liquid, increasing porosity and height of the bed. As we said, obviously, if we go on increasing this, then this height will go on increasing like this, or then further like this, right, or then further like this, or then maybe even further like this, right. So, this will go on increasing, and as we said, after some time, if still we are going on, these particles will start moving and they will be transferred to from one place to other place, and this is called that this we have said earlier, and this condition is called your conveying or pneumatic conveying. When you are using air, we call it to be pneumatic conveying as the medium, right. So, then what we have understood that before the onset of fluidization, we have a porosity, we have a velocity, we have a delta P, we have a height of the bed. Under that situation, as we are increasing the velocity, there will be a minimum velocity at which the particles will start moving as if all the particles are floating on the medium, that is the fluid which is flowing through that, and the particles appears to be like just dancing, right. This condition is known as minimum fluidization condition. Corresponding parameters like height of the bed is LMF, velocity is Vmf or Vmf prime, void is epsilon mf prime. So, these and your delta P is delta P mf, right. So, this way all the parameters will get changed, right. So, we will see subsequent classes how we can find out how much change in the height, what is the velocity, etc. Right. Thank you.